All right, we're going to begin chapter 19, magnetism. Let's bring up the PowerPoint. Magnets are fascinating, very useful also. Electromagnets are used to pick up heavy loads. Magnets are used in meters, motors, and loudspeakers. Magnetic tapes and discs are used in sound and video recording and to store computer data. Intense magnetic fields are used in magnetic resonance imaging, or MRI. I used to work in a nuclear magnetic resonance lab, no imaging, but just looking at the free induction decays of different materials. And we had very, very strong magnets. The list goes on and on. Magnetism is linked to electricity. Magnetic fields affect moving charges, and moving charges produce magnetic fields. Changing magnetic fields can even create electric fields. In this topic, we will explore magnetism and its relation to electric current. And here is there it is. Here is a horseshoe magnet. You've played with those. You've played with them in the lab. But in our investigation, we're going to stick to the bar magnet, like this one shown here. For our discussion, we will be focusing on bar-shaped magnets. Iron objects are strongly attracted to either end of a bar magnet. The ends are called its poles. One end is called the North Pole and the other the South Pole. You might wonder where these names come from. Imagine a bar magnet suspended from its midpoint by a piece of string so that it can swing freely on a horizontal plane. The magnet will rotate until its North Pole points to the north and its South Pole points to the south. The same idea is used to construct a simple compass. Magnetic poles exert attractive or repulsive forces on each other, which is similar to the electrical forces between charged objects. In fact, simple experiments with two bar magnets show that like poles repel each other and unlike poles attract each other. There is one very important difference between electrical forces between charged particles and the behavior of magnetic poles. Positive and negative electric charges can exist in isolation of each other. North and south poles don't. No matter how many times a permanent magnet is cut, each piece always has a north pole and a south pole. There are some theoretical bases that magnetic monopoles, isolated north or south poles, exist in nature, and the attempt to detect them is currently an active experimental field of investigation. It was in one of the recent Physics Today magazines that I get that they're hotly pursuing magnetic monopoles, but personally, I don't think they're going to find them. Soft magnetic materials, such as iron, are easily magnetized but tend to lose their magnetization easily. These materials are used in the cores of transformers, generators, and motors. Iron is the most common choice because it's inexpensive. Other magnetically soft materials include nickel, nickel-iron alloys, and ferrites. Ferrites are combinations of a divalent metal oxide of nickel or magnesium with ferric oxide. Ferrites are used in high-frequency applications such as radar. Hard magnetic materials are used in permanent magnets. These magnets provide magnetic fields without the use of electricity. Permanent magnets are used in many devices, including loudspeakers, permanent magnet motors, and the read-write heads of computer hard drives. There are a large number of different materials used in permanent magnets. Alnico is a generic name for the various alloys of iron, cobalt, and nickel, together with smaller amounts of aluminum, copper, or other elements. Rare earths such as samarium and neodymium are also used in conjunction with other elements to make strong permanent magnets. Okay, as you recall, an electric field surrounds any stationary electric charge. The region of space surrounding a moving charge includes a magnetic field. A magnetic field also surrounds a properly magnetized magnetic material. In order to describe any type of vector field, we must define its magnitude or strength and its direction. The direction of a magnetic field B at any location is the direction in which the north pole of a compass needle points at that location. The figure on the left shows how the magnetic field of a bar magnet can be traced with the aid of a compass, defining a magnetic field line. We sprinkled iron filings onto magnets and could see their magnetic field lines. In the figure on the right, a couple of magnetic field lines are traced out. Of course, here the field lines are shown in 2 dimensions. In reality, they exist in 3 dimensions. We can see the patterns produced by magnetic fields by placing small iron filings in the vicinity of a magnet, as in the figure shown. The left-hand figure is a single bar magnet. The middle figure is 2 bar magnets with unlike poles near each other. And the right-hand figure shows the interaction of like poles. Forensic scientists use a technique similar to that shown in the figure to find fingerprints of a crime scene. One way to find latent or invisible prints is by sprinkling a powder of iron dust on any surface. The iron adheres to any perspiration or body oils that are present and can be spread around on the surface with a magnetic brush that never comes into contact with the powder or the surface. Okay, this ends our section on magnets. The next section is section 19.2, Earth's magnetic field.